So I've changed the title a little bit, but it's the same talk more or less. So thanks for the invitation and showing up for the talk at such an early time. So I'm basically going to talk about some work that I've been doing mostly with some of my students in the last, let's say, 2 years or so. It's still kind of an ongoing process. We don't fully understand everything, but I'll try to tell you what we have been doing. So yeah, so this is so this Vishal and Pradeep and Vaibhav are my students, and so Chethan was the postdoc who was with us for an year. So, and this is work done in collaboration with them. Okay, so I'll basically try to motivate it like this. We know that black hole horizons in general necessarily have entropy. So, and this entropy is in classical gravity unaccounted for, in the sense that if the horizon is part of the description of a state, then we know that it is going to have unaccounted entropy. So, which essentially is, by definition, it means that conventional horizons cannot be part of the description of a black hole microstate, because microstate by definition means that it has no entropy. It is essentially a single state in the Hilbert space. Okay, so that's sort of the starting point. And so, but understanding bulk microstates of black holes seems essential for a satisfying resolution of the information paradox. And we have made various bits of progress on the information paradox, but it's a Lorentzian problem. In the sense that we are really concerned about how time evolution of states, individual states, happen. And even though we have computed recently in the last few years, computed the page curve starting from Euclidean path integral type arguments, these really require the assumption of approximate equilibrium at which epochs in Hawking's evaporation. And it's to be fully, so it's essentially tracking single numbers in the sense of certain entropies, but not really a full understanding, or even the nature of the evolution of the state we don't fully understand. So, of course, even in general thermal systems, we don't fully understand the full microscopic details of a state, but nonetheless, we have a picture of what is happening, and that is still lacking in the case of black hole information paradox. So we know, based on this Euclidean argument, that overwhelmingly likely the state is pure at the end, but we still do not have a completely satisfactory understanding of the Lorentzian time evolution. Okay, so what is the mechanics of information coming out of the black hole? So, and for that, you will need some sort of a Hilbert space type description, because Hilbert spaces are where things evolve, and the Lorentzian description is intimately tied to a Hilbert space description. So that we would like to have. So at least some sort of an understanding of it. Unfortunately, currently we have no top-down construction of finite temperature black hole microstates in string theory or in string theory. So, and this is, it's the crucial point is that in order to fully understand Hawking evaporation, we need to know time evolution of some microstates in some sense, some at least qualitative understanding of the time evolution of such states. So given the state of affairs, we can ask, can we engineer an instructive picture of a bulk microstate using bottom-up arguments? Okay, so instead of like in string theory, usually the kind of microstates that we construct, we don't still have access to the typical microstates, even in the case of BPS black holes, in the bulk, the side of the duality, ADS-CFT duality. But we can engineer, but especially in the case of black holes which are finite temperature and which in particular break all supersymmetry, we have no understanding at all of the bulk microstates in general. So at least in any kind of useful way. So what I have in mind when I talk about this is that, like, for instance, when we talk about a gas in this room, so we don't have a fully standard model UV complete quantum gravity description of the gas. What we have is we have a model which is hard spheres or whatever, and the statistical mechanics of these hard spheres, from that we are able to intuit what is going on regarding the thermodynamics of gases, and we feel that we understand the system well enough. So something analogous to that is what I really mean by engineering an instructive bottom-up approach to black hole microstates. Okay, so the question is, where do we even begin? So, and there are so we can start with some possible broad demands that we have, and if such demands are not met, I mean, this program will not even lift up from the ground. Okay, so first demand is that we want to work in Lorentzian signature. This is essential for the reasons I mentioned earlier, which is that we want Lorentzian evolution to have some understanding, and we ultimately want a Hilbert space of states. So, for even in the case of these supergravity fuzzball solutions that people have constructed, leaving aside the fact that they're perhaps not typical, even leaving aside, there is this problem that, yeah, so even there, it's not a Hilbert space of states. These are basically supergravity solutions. Okay, so there's classical solutions which may or may not be reliable, but the point is that it's not a Hilbert space of states, and we would really like to have a Hilbert space of states if possible in order to get some idea of the quantum evolution of the system. Okay, and we want to be away from supersymmetry extremality, as I already mentioned, and we would like to work with ADS-CFT, because in ADS-CFT we have some intuition for what bulk states are in terms of what the CFT states are. Okay, so by the way, please, I mean, this is a little cozy group, so please feel free to interrupt me at any point. I don't even necessarily have to get to the end of the talk. So by all, please stop and ask if there is any questions, even if they're too basic, because I see many PhD students here. So, and the final ingredient is that for starters, it seems reasonable to try to understand a microstate of a black hole. In the case where the black hole is, we are really talking just about the black hole in some sense, and not about treating the black hole as an open system, which would mean that you're looking at a black hole, small black hole in ADS, which can ultimately evaporate. So that would be a nice, interesting step to do in order to understand the page curve and actual time evolution of this black holes. But it will be a good start if we could just understand a finite temperature large ADS black hole which is in equilibrium with its own radiation. Okay, so in ADS is like a box. So if you have a large black hole, the black hole is basically in equilibrium. Okay, so and you can think of it as a black hole. It's not a closed system. Sorry, it is a closed system as opposed to an open system, which is what you have in flat space or if the black hole is small. So, therefore, our first natural target is to try to get a bulk picture of a heavy microstate in the conformal field theory that is dual to this holographic, to ADS. So these are the microstates of a large ADS black hole. And the question that we are going to try and ask here is there a way in which you can bottom-up construct or engineer a heavy CFT microstate which might have some of the features that you would like from black hole while being in a quantum mechanical system? Okay, in classical general relativity, we of course know that you can get black hole thermodynamics and you can compute correlators with infalling boundary conditions of the horizon outside, and then you get, you can compute correlation functions, and you can get thermodynamics and various things like that in classical gravity or classical black hole backgrounds. But we would like to engineer it as a Hilbert space system. So this is what we would like to have. So the question, so if you want to do this, clearly we don't have access to full string theory, not perturbative string theory. So, we will have to start somewhere. So the questions that I'll set it up like this. So I'll give you an overview of some of the things that we did, and then kind of, this is not very heavy on equations. So you can look at the papers if you like, but I'll give you an outline of the story because it's a somewhat lengthy story, and then I'll present some equations which are kind of clear, or at least easy to understand more towards the end. Okay, so should we completely give up the metric? This is one question you could ask if you want to model a bottom-up model for a black hole microstate. And that's a real possibility, because we might want to give up the metric because in finite n, these are, Planck scale being finite in the bulk basically means in the dual CFT that you're working with finite n in the gauge theory. It's no longer in the large n limit. So, and that seems to suggest that in many cases we do know. For instance, in a couple of years ago, maybe last year, even in the case of these in the matrix models and so on, people have constructed sort of bulk duals which are not in continuum space-time. Okay, so there is this work of Gautam Mandal that I'm thinking about, and so it seems to suggest that some sense that if you are in finite n, the natural description is not entirely a metric description. Okay, so and it's sort of intuitive anyway. And but the reason why, but if you want that, then we are already lost, because there's no possibility of any understanding. But the reason why it may not be necessary is because the metric description by itself is not what is causing unaccounted entropy. So the reason why we have unaccounted entropy or microstates which are inaccessible is because we have horizons. And so maybe it is the horizon is that we can get rid of the horizon in some way and try to get an understanding of so try to construct a bottom-up model for microstates. So a key point is that the principle of equivalence, which is an EFT statement, it's an effective field theory statement. Okay, in order to make the statement that the principle of equivalence holds, we are already at that stage. We are in effective field theory, and not having a UV complete, not having a smooth horizon in the full UV complete description is not immediately a contradiction with principle of equivalence in the effective field theory. And so this is kind of related to the, so for instance, you can think of, like often this, we'll ultimately be going for a model which has a stretched horizon or a, something that cuts off the horizon in some way and then try to construct a Hilbert space in some way. That's what we are going to do. So, but this is not immediately, what I want to emphasize is that it's not immediately a contradiction in, if you want to talk about black hole interior, etc., that's one thing. But at the very least, you should be able to get correlators in the outside of the black hole in the low energy limit, which are indistinguishable from the correlators with a smooth horizon, if you want to protect the equivalence principle outside of the horizon at the very least. So this is like a minimal requirement that we have to have. Okay. So and the goal of this talk is basically to take some explicit steps in this direction, and we will argue that exterior correlators, by exterior correlators I mean correlators that are outside the horizon of a black hole, are exponentially indistinguishable, and exponential in the black hole entropy, indistinguishable from smooth horizon correlators in these toy models that we are going to construct. Okay, so this is the point. So there are two hints how one might go about it. Firstly, as I said, we are interested ultimately in these large ADS black holes. These heavy microstates are in some sense in equilibrium with its own radiation, because if you put a large black hole in a box, what you would find is that the radiation goes to the boundary and comes back, and if you can have eigenstates which are black holes, or at least eigenstates which are black hole microstates. So this is what you imagine in the ADS-CFT picture of what a black hole microstate should be. So the idea is that if the black hole is in equilibrium with its own radiation, then it's not just the black hole that you would have if you are looking at states in the Hilbert space of this theory, but you will also have radiation in it. Okay, so that's necessary for the system to be in equilibrium. And secondly, and equally importantly, there is a large negative stress tensor at the stretched horizon. Okay, so yeah, so this is essentially, there are many ways to phrase this, but very roughly it is the idea that if you put, if you install any kind of stretched horizon, so we are going to cut off the horizon and then try to model it some way. So if you if you do that, then the point is you're breaking anything at near the horizon wants to fall in, right? Because that's the principle of equivalence. So, and if that leads to a negative stress tensor, there's essentially you need to support it somehow, otherwise it is not going to stay where it is. Okay, so this is often it's a one big reason why people don't like the idea of things like stretched horizon. Okay, so, and this is in some sense you can think of it as an Einstein penalty, which is that if you put up a stretched horizon, it will want to fall in, and you somehow have to prevent it from happening. So one interesting observation that was made, I think it is almost 20 years ago now, maybe even around the time of ADS-CFT, I think. So by Israel and Mukoyama, is that one way in which you could, bypass this problem. Bypass this problem of this Boole-Ware vacuum type problem is that you can dress the system with a radiation fluid. So they just postulated a fluid of some radiation on top of this. Once you install the stretched horizon and you have this radiation fluid on top of it, then they notice that this can cancel the negative divergence created by the stress tensor, the negative divergence created by installing the stress horizon. So we'll take it as sort of a jumping off point for our stuff, which is that, well, that's not quite the way we arrived at this thing, but this is a good place for us to start for the purposes of this talk, is that both problems have the same solution. By both problems, I mean the fact that the ADS, heavy ADS microstate, it seems to be in equilibrium with its own radiation, and the fact that the negative stress tensor of the stress horizon can be balanced by the radiation fluid, both have the same answer. So radiation seems to be precisely what is missing, and in order to support this thing. So that gives us a point of view on how to potentially construct microstates, is to interpret the radiation as a highly excited state. And this is sort of the main statement that we are using, we'll be developing, is that interpret the radiation as a highly excited state of the quantum fields in the background of the stretch horizon. So what I mean is that you have a black hole with a stretch horizon, and now you can quantize fields with the boundary condition of some Dirichlet. It doesn't really matter what the boundary condition is as long as it is not dissipative. So you can put boundary condition at the right outside the horizon, then quantized fields outside it, and then you can look at a highly excited state of those quantum fields. And I'll specify how exactly we pick those states, etc., in a minute. So it's not the stretched horizon vacuum that should be compared against the black hole microstate, but a typical state in the Hilbert space of this quantum field theory with an energy that is asymptotically measured as to be the mass of the black hole. Okay, so you do a quantum field theory with the stretched horizon, let's say in ADS, and then you look at a highly excited state. So, and this highly excited state is one that is whose energy is asymptotically measurable, because note that we are quantizing the fields in the exterior of the black hole. So the time coordinate is the boundary time coordinate. Okay, so which means that the energy that you're measuring is the asymptotic energy. So what happens is that if you do that, so the claim is that such a state with energy at that sliver is basically a candidate for the black hole microstate. So this is the picture that we're going to use, and we'll try to explore various things with it. So if you have any questions, I can, if the picture is not clear, I think I'll clarify it a bit, but if not, we can go ahead. Okay, so this is basically a sort of a Hilbert space realization of this radiation fluid picture of Israel and Mukoyama. And the key observation is that demanding that the energy of these modes measured asymptotically is the black hole mass is basically defines an ensemble for you. Okay, because it's a highly excited state, so you get, just like in standard, let's say, Planck's calculation, if you fix the energy or the temperature, then you have defined an ensemble. So there's a lot of microstates which fall into that sliver. So, and from that definition of the ensemble, once you specify the mass of the black hole, you can, literally directly compute in this quantum field theory what the entropy and temperature should be. Okay, so this is just a statistical mechanics calculation at that point. And so you find, so this is, I'm kind of outlining sort of the punchlines first. So in case you fall asleep towards the end, it doesn't matter. So you find that you can reproduce the Hawking temperature exactly, and you find the Hawking temperature, the entropy, up to one caveat that I will emphasize in a second, that you can reproduce both these features directly. So once you specify the mass of this, the mass of the energy of this state in the Hilbert space of the quantum field theory with a stretched horizon, what you find is that the temperature and the entropy of the black hole can be computed by direct statistical mechanics calculation. Okay, so there is a one parameter freedom in this calculation, which is basically related to the fact that we have, that's where our lack of knowledge of the UV complete system comes in, which is that we don't know, there is some structure at the horizon, but we don't know how, it's a stringy input. We don't really know what it is. So there is a freedom in adjusting the location of the stretched horizon. And that freedom we fix by, matching the numerical coefficient of the area. Okay, so the point here is that this numerical coefficient, so I want to emphasize that the area scaling comes out of the calculation, but the numerical coefficient is unfixed because we don't have the knowledge of where exactly the stretched horizon is. So you adjust the stretched horizon location so that that coefficient comes out to precisely match the Bekenstein-Hawking result. So, and the temperature basically then follows by standard statistical mechanics. Okay, so this is the overall picture, and I will So this can be viewed as a revision of the old Toft brick wall idea. Brick wall is another old name for the stretched horizon. So I think this is the first paper where from 1982 or something, where the idea of a stretched horizon first came up, and we are essentially taking it seriously and how far we can push it. That's what we are really doing. Okay, so the picture of that is essentially so the way Toof did the calculation I'll outline in a second, and because we are computing, so he did not compute the normal modes. So if you have a quantum field theory with a stretched horizon, you can compute the normal modes of the system, and that's how you quantize it. Just like if you have a black body, if you have a box, you have fields inside it, you look at the standing waves, you second quantize it, and that's how you get the Hilbert space, right, in Planck's calculation. In exactly the same way, it's ADS. ADS is a box. You have put a stretched horizon here, now you're in a box. Okay, so you can quantize the system, find the standing waves, and second quantize it. The claim is that the state in the Hilbert space with energy m, which is the mass of the black hole, is basically what defines the microstates of the black hole in this sort of bottom-up approach to this. So we have to, the challenge is basically to compute these explicit normal modes. So Toft managed to, Toft's calculation is not quite phrased in this way, but I'll kind of outline it from our point of view, which the Toft counts only the semi-classically allowed modes, because so what he did was he also looked at scalar fields in outside the black hole with a stretched horizon. This was in flat space. Various things are different, but I'm phrasing it in a language which is adapted to ADS CFT. So what he looks for is the semi-classically allowed modes. What semi-classical means there is that the radial wave equation, the radial part of the wave equation of a scalar field or any field, basically will contain a potential term, right? In the radial, or sometimes it's called the angular momentum potential. So this angular momentum potential, so you only look at modes which are in the classically allowed region of this angular momentum potential, and that is what Toft essentially did. And the motivation for doing this is not completely clear to me, but it does the job. So that's how he does the calculation. And if he did not do that, then he would not be able to do the calculation. But seems like a technical trick, but it gives answers which are close enough. So in that sense, maybe there is something deep there. So the way he did the calculation then was that he did not compute the normal modes. Okay, so you have a scalar field outside the black hole horizon. You have a stretched horizon boundary condition. In our case, normalizability at the boundary. And then we are just looking for standing waves of this. Okay, and these standing waves, instead of computing that, what he did was that computing these normal modes systematically, he used the semi-classicality argument to kind of indirectly argue things about the system using a Bohr-Sommerfeld type of approach. It doesn't matter to us, but I'm saying that he puts in semi-classicality as a tool for avoiding the explicit calculation of the normal modes of the system. So, and by doing that, he managed to get the area scaling of the entropy. Okay, so, but there are a couple of things that could be improved if you want to take this very seriously. Okay, so we are going to take it as seriously as possible, and how far, where is it going to break, is what we want to find out. So his calculation was indirect, as I just mentioned, and he did not determine the modes explicitly, and he only looked at the semi-classical modes. So because of which he had to specify both the temperature and the mass or the energy of the system, of the black hole. Okay, and then he got the area scaling. So this is the way he calculated it. And essentially that's because he doesn't know what the normal modes are. So there's one degree of, it doesn't, so that means that he had to kind of put in both these macroscopic parameters into the problem. And this is not what one would typically do in a real, genuine statistical mechanics calculation, because if you specify the mass or the temperature, you specify the ensemble, and the rest should be calculable, right? So that's there's nothing inherently incorrect about it. It is just that he, in order to substitute his lack of knowledge of the normal modes, he had to specify both these things. That's what he did. So, but on the other hand, so if you want to really check whether this is a really genuinely statistical mechanics valid thing, so you would like to actually reproduce the temperature and the entropy both from just specifying the answer. Yes, please go ahead. Yeah. So I think two boundaries. One, because we have some condition at the stretched horizon. And then the second one in ADS, we have a normalizability condition. Absolutely. Absolutely. And it is crucial that that is the case because we want to be able to measure everything at infinity. So I'm glossing over some features here, which is that, for instance, Tooft is doing his calculation in flat space, so there are various slightly ad hoc things that he has, what I would call an ad hoc things that he has to do. But in ADS, this becomes a completely precise calculation, if you are looking at a large ADS black hole, because we have normalizability at infinity and some non-dissipative boundary condition at the horizon. We'll take it to be Dirichlet, but the details don't seem to matter too much. Yeah. Sorry, can you? That's right. Different mass black hole. That's a good question. So the point is, note that we are working with a setup. So it is crucial for our picture that we are working with so this is not quantum gravity, right? That's why it is a bottom up approach. We are not working with in a system where the energy of the black hole itself, the mass of the black hole, is not obtained from starting from the CFT vacuum and just populating states. That's not what we are doing. What we are trying to find is, so let's say this is the CFT, and this is some sliver of, or let me call it M to make it look more like a black hole. So this is some sliver of states. And in the bulk, I know that, classically, the black hole geometry is given by some Schwarzschild mass, right? So I take that, but what I do not have access to are the actual microstates. How do I associate a bulk Hilbert space to this sliver? This is my question. So in order to do that, what I start with is I will start with the black hole spacetime with this mass. But then the claim is that we have to cut it off right before the horizon, and the fields in the bulk which are fluctuating are the ones which contribute to the states in this line. So which means that it is crucial that we are working in this sliver to start with, so that the background that we are working with is the black hole with that particular mass. That's crucial. So if you want to change the background itself, right? So which is basically corresponds to changing the sliver, then you have to work with the corresponding M prime mass black hole. Okay, so that's what we do. And then the claim is, but what is interesting is that even in a given background like this, the asymptotic energy is just the asymptotic energy. So you can measure that energy as the excitation states. So in some sense, the redshift at the horizon is together with the compensation from the energy of the excited states seems to be what is giving the total answer. So, but yeah, we can discuss it. It's an interesting question. Yeah. So the point I want to make is that this is we are trying to construct the states using quantum field theory in third space with some hocus pocus. That's what we are trying to do, right? It's not a fundamentally quantum gravity construction. So, yeah. Okay. So, any other question? Yeah. How do you? So this is because if once I have a black hole metric, the time in the Schwarzschild coordinates is the asymptotic CFT time, right? So the conjugate energy just measures the energy of the black hole. So it is crucial. So what I'm basically saying is that if you cut off the black hole, so what people often used to do is that, let's say you have a black hole sitting here and you cut it off here, right? So this object as it stands without any excitations is not a meaningful object in the CFT. So the moment you cut it off, it's crucial if you want to mimic the black hole that you excite. You also simultaneously consider the excited states at the mass of the black hole, because this is coming with a negative divergence stress tensor, as I was saying, because the moment you cut off the geometry right outside the horizon, there is a negative divergence. So if you don't, so immediately the interpretation that this geometry has an energy of mass m is gone. So now that crucially relies on the existence of the horizon. So once you remove that, you better do something to make sure that the system has energy of equal to the mass of the black hole, and that's what this dressed this excited states at energy m do. So the claim is basically that it is inconsistent to just cut off the geometry by itself. You need to necessarily also dress it with this excited state with energy m. So that's what makes the system like the microstates of a black hole of mass m. Uh-huh. Measuring the mass of a black hole within the bulk is a difficult question, even in classical GR, right? So it's an asymptotically defined charge. Yes. So the mass, so for instance, like if you're, so the QFT in curved space that I'm working with is quantized with Schwarzschild time, right? So the energy of the excited state is precisely the energy that is measured asymptotically. Because so I'm working with, let's say if you're working with, I'll show you the example of BTZ or something. So if this time is directly measuring the asymptotic time, that is the CFT time. So which means that if I measure energy using this, that will automatically translate into the energy as measured by the CFT. See, so the asymptotic charges and all of that is in GR, right? We are working with a fixed background. This is quantum field theory in curved space, which is, so if you want, so you can do, if you want, you can do the in the GR kind of setup. That's a statement about how the space-time's energy is measured in GR in terms of boundary integrals and so on. That's dynamical gravity. That's not what this is. We are trying to model a sliver, which is a quantum field theory in a fixed background. How to do that consistently if we have a stretched horizon? That's roughly the question. So asymptotic charges would be a GR question. We are not fluctuating the geometry itself. Maybe we can discuss later. Yeah. So yeah, sure. Yes. That's right. And that's a great question. And that's related to the fact that I mentioned, which is that if I cut this thing off here, there is a negative divergence stress tensor. So what I'm saying is that I need to put this in, so that the system is, if I just cut off the structure here, right? There's a negative divergence stress tensor. So the system doesn't have a well-defined mass from the CFT point of view, because we have done something drastic. See what I'm saying? So, and then you need, in order to, what this automatically accomplishes is to compensate for that divergence by dressing it with radiation. So the claim in some sense would be that if you want to have microstates, right, which are at the mass of the black hole, then you cannot, and if you want to have any kind of model for microstates which is based on stretched horizon and so on, then you must dress it with radiation so that the mass of the black hole stays where it was. So otherwise, the cutting off the geometry is actually such a drastic event that it's no longer meaningful to say that the geometry has mass m. So the moment you cut it off, the dressing is necessary so that you're staying where it was, but without the horizon. So it's kind of related to this Boulevard vacuum thing that I mentioned and the Israel Mukokiyama solution. Sure. That's right. Yes. The Hamiltonian is that of a quantum field propagating in that background. Exactly. So that's right. That's it. So yeah, so it's basically just the standard quantum field theory in curved space kind of thing in ADS. And the question, I think, somehow, I think many of you are sort of asking is that once I remove the stretched horizon, if I build up so much highly excited state, into this geometry, how can I ignore the back reaction? I think that's what you're asking, all of you, in some sense. But my point is that once you cut off the stretched horizon, right? Once you cut off the horizon, then it already has a negative divergence stress tensor. So if this is not there, that is the problem. You see what I'm saying? So if I cut off the stress tensor, if I want to install a stretched horizon here, it is going to create a divergent stress energy, divergence in the stretched horizon size already. So if I want to make sure that the geometry stays where it is, I'm actually compensating for the back reaction by looking at the excited states. That's what I'm really doing. Okay, so this is, I think it may take a little, so let me go ahead. So I think, you can ask me questions as we go. So, so it's basically a cancellation between what could have been a divergence versus this excited state that I'm putting in. Okay, so that's the original idea of Israel and Mukoyama, where they noticed that dressing the system with radiation is enough to cancel the divergence that shows up because of the stretched horizon being, stretched horizon. Okay, so so let me go ahead with the distinctions from the Toftian calculation. So this is what we are doing. So because we compute these explicit normal modes by doing hard work, by looking at the radial equation and solving it with these boundary conditions, we can in principle compute the statistical mechanics straightforwardly. With this, the entropy becomes less mysterious. So one of the observations that we have is that if you compute these normal modes, the J quantum numbers of the system. So there is angular directions in this geometry, right? These angular directions in the geometry the J quantum numbers become almost degenerate. Okay, not exactly degenerate, but approximately degenerate. And that's ultimately what is responsible for the entropy of the black hole, as we will see. So this is, I would say it is not as transparent because of the indirect calculation of Toft, but here it is very clear that unlike for instance, in ADS or in flat space, if you computed normal modes, what you would find is that you would have a linear spectrum in N and J. N being the principal quantum number type of thing, and J is the angular quantum number. But here, if you put the cutoff there, you find that the J quantum numbers become approximately degenerate. So, and this is ultimately what is responsible for the entropy. And this is fundamentally the difference between Planck's calculation and Toft's calculation. Okay, the Planck's calculation, if you just put it in a box, you will find that there is a quantum number associated to every spatial direction. Okay, so there is nx, ny, nz in standard Planck's calculation. But here what happens is that because of the infinite redshift at the horizon, one of the quantum numbers gets pulled down. So it essentially becomes degenerate. So effectively the problem reduces to the gas in one lower dimension. So that's essentially what happens, and that's the reason. So it's kind of seeing the normal modes explicitly kind of drives it home very clearly that that's what the mechanics of it is. Okay, so another structural improvement from Toft. So now I think slowly I'll get a little more technical. So another structural improvement Toft that we have recently incorporated is that Toft defined the stretched horizon by measuring things from the horizon. So he measured things to be a Planck distance or a string distance or string length or whatever from the horizon. But in ADS-CFT, you would like to anchor things to the boundary because that's what is somehow gauge invariant in the gravitational sense. So, and that we can do. Okay, so one way to define that is that if you are measuring the energy of you define the stretched horizon or the brick wall as the location where the energy of a CFT mode becomes some UV cutoff in the bulk. Let's say you have a Planck scale in the bulk. You say that this is the location at which the CFT mode omega. For any omega, there will be a particular location because of the blue shift at the horizon where it will actually equal Planck scale. So this is a kind of a natural definition for, even independent of everything I'm saying, I think it is a natural definition for what the CFT sees as the location of the horizon in some sense. Because for any given energy of the CFT mode, there is a particular location at which that crosses the Planck scale. And that's always, and if you explicitly calculate it, you find that this is essentially very close. I mean, it changes with omega, but it doesn't change the physics that comes out of Toft's calculation. Okay, so that's the sort of the point. So I'm not going to elaborate it too much. So that's the, so what is interesting about that is that even if you work with these kinds of modes, which are holographically anchored rather than horizon anchored like Toft was doing, you find that the basic physics remains intact. Okay, and so I will, so another thing is that if you, this is again some technical comments. So Yeah, let me actually skip that for now. How much time do I have? 15 minutes. Oh, I haven't even gotten to the. Okay, so we have. Yes. So let me just skip this. Yeah, so the general story is that, okay, so you can do this and you get the statistical mechanics of the system, and with this one freedom in the location of the stretched horizon, which is a UV input. Okay, so the rest of the things I said, the caveats that I was mentioning here do not affect that statement. So so the point is that now the thing is that because we have computed the normal modes explicitly, right? So because he didn't compute the normal modes, Topes only could do statistical mechanics and thermodynamics at best. And but because we know the normal modes and we have an explicit quantum field theory sitting outside the horizon, we can compute its correlation function. Okay, so if you compute these correlation functions, how much do they depart from the Hartle-Hawking correlator, which corresponds to smooth infalling boundary conditions at the horizon? Okay, so that's the question. So if you did all this and you computed the correlation functions and they are vastly different from Hartle-Hawking, then this cannot possibly be an acceptable set of microstates for the black hole. Okay, because we know that at least far away from the black hole, the correlator should reflect the fact that there is what looks like an infalling boundary condition at the horizon. Okay, so this is one thing we have to do. So we can explicitly, but the point is that because we have this explicit system, we can quantize these things and compute the correlators very explicitly. Okay, so consider so this is what we do. So essentially we take the scalar field or some field, it doesn't really matter. So, and we compute quantum fields, we quantize the fields with Dirichlet boundary conditions, let's say at the horizon, and look at states at this energy, and that gives you a ensemble of QFT states. And what we find is that these stretched horizon correlators turn into the Hartle-Hawking thermal correlator as the L Planck is tuned to 0. So as you push the stretched horizon to the horizon, you find that this it becomes indistinguishable from this. Another way of saying the same thing is, actually maybe a better way of saying this is that if you compute the correlation functions, they are Hartle-Hawking correlator plus an exponential correction in entropy, e to the minus, it's suppressed by the corrections are suppressed in e to the minus SBH. And this is actually a good thing. The corrections are obviously very small, and note that e to the minus SBH is an extremely tiny number. It's not perturbative in 1 over n. Okay, it is non-perturbatively small in 1 over n. And and it has, it's naturally what you would expect from something like eigenstate thermalization, which is that if you take a light operator in a heavy state, it should look thermal up to exponentially small corrections in the entropy. And that's precisely the structure that we have because we have a explicit statistical mechanics system. Okay, so so that's the general story here. So it's a little bit of a crowded slide. So because Hartle-Hawking correlator is usually viewed as an indicator of smoothness, and the reason is there are two reasons for it. One is that one way to understand that is that it essentially comes from quantizing in Kruskal coordinates. Okay, so that's essentially the reason why you get the Hartle-Hawking correlator. It's a particular correlator for scalar fields outside the horizon, if you haven't seen it. So, and it basically comes from taking Kruskal coordinates seriously. That's the reason why you get it. And Kruskal coordinates are by definition what guarantees or what is a consequence of assuming smoothness across the horizon in the sense of the principle of equivalence. So if you have a smooth horizon, then you're guaranteed to have Kruskal-like coordinates. Then you can quantize your fields using those, and then you find that the correlation functions are the Hartle-Hawking form. So the fact that we are finding the Hartle-Hawking form plus exponentially small corrections means that smoothness, in some sense, is an emergent phenomenon here. And another reason for taking the Hartle-Hawking correlator as a sort of a measure of, or as a proxy for smoothness, is that you can construct interior operators using these thermofield double constructions and analytic continuation. There are various ways in which people have constructed them. All of them are directly accessible when you have this kind of a thing. Yeah, let me just skip this slide. I think it is. Yeah. So yeah, I'll just speak. Yeah. Okay. Let me say this instead. Yeah. So so one interesting point is that oftentimes in thermal states, people will construct, you can construct a thermofield double. Okay, so you can construct a thermofield double construction of a thermal correlator. But the second tensor factor in the thermofield double often does not have a very good physical interpretation in conventional, in standard quantum systems. One of the remarkable things about the black hole is that in the context of the Hartle-Hawking correlator, the thermofield double has an interpretation as the second tensor factor of the Penrose diagram, right? So this is something that you may have seen. And the interesting thing is that because we have a connection with the Hartle-Hawking correlator, that interpretation is accessible to us. How seriously one should take it is a separate question. We can analytically continue the Hartle-Hawking correlator and find the other regions of the Penrose diagram if we wish. But, so what exactly happens to infall, etc., I think there are new ideas are required. But, so let me also say, those who have are familiar with this recent discussion in this Loithoiser-Liu type of papers, where in the large n limit, there's a transition from this so-called type 1 algebra to a type 3 algebra. I'll say a bit more about that eventually. So this is sort of a bulk version of that. Okay, so if you put a cutoff and the cutoff going to zero limit, note that the cutoff is very directly a measure of the finiteness of n, because it's a bulk Planck length. So, and if you take it, drive it to zero, n is going to infinity, and that's precisely the setting where you expect the transition from type 1 to type 3 algebras in the setting of Loithoiser-Liu and those sort of things. And that basically means that there is a second tensor factor. So I'll come back to that in a second. So I just keep that in mind. So now let me just, since I said this outline, I was not quite sure how to organize the thing because it's based on it's an overview of many papers in some sense. So let me just say, now I'll give you a brief outline of the calculation a little. I think now it should be a little bit more clearer. So let's take the example of BTC. Okay, and we are doing scalar field theory in the BTC background, and we impose a cutoff like this at some small epsilon near the horizon, and we demand normalizability at boundary. Okay, so this comment is based on upcoming work, which I mentioned about anchoring the cutoff at, holographically. And so determining these normal modes with these kinds of boundary conditions is complicated. Okay, so if you typically what you demand at the horizon is infalling boundary condition. And then you can compute the solutions as standard solutions of wave equations and so on. So, but here it is more complicated. But the saving property that makes the correlators calculable is that, as I said, in the very low-lying part of the spectrum, which contributes to the black hole thermodynamics, in that region, the spectrum has this form very roughly. The omega 0 doesn't matter what it is; it's some constant, and it's approximately degenerate in J. Okay, so this is what allows us to calculate things explicitly, because otherwise the actual numerical form and even the analytical form of the spectrum is more complicated in the analytically solvable part of the spectrum. So this is the key input that we will use in our calculations. So yes, so in all this talk I have really only talked about, I will only talk about thermodynamics and computing Weightman-like correlators, but it should also, I should briefly mention, because I've worked on, with many of my collaborators on things which are related to chaos and random matrix-like properties. So if you take this spectrum, this omega nj that I just wrote down here, these guys explicitly we know. Here I am only keeping the most crudest features of that, which is basically that it is approximately degenerated at low energies. But if you actually look at the actual form of the spectrum, you can compute all things which people are interested in, the level repulsion, the ramp, in all of those things. I mean, if you have seen these things in the context of this chaos and random matrix type discussion, you will find that all of those things are actually, you can get indications of that. It is difficult to do these things completely, under control, because the spectrum is not very accessible to us. But all of these features have reflections in them. Okay, so that's the statement that I just wanted to make as a passing comment. I didn't want to offend my collaborators. So let me come back to the story, which is basically that with these boundary conditions, you just do quantum field theory in this background. It's straightforward. And, these are just the modes I'm writing in some way. So then I expand the fields in this way, just like in flat space or anywhere. And the key point is that the stretched horizon vacuum is defined with this annihilation condition. And the states that we are going to look at are some highly excited states of this type. And we are going to ensure that the energy content of these states is the same as the black hole mass. So that's what we are going to demand. And there are some technical issues which you have to handle because once you have a cutoff, you have to redo various things. So and they become somewhat more complicated. But once you do all these things, this is the demand on the excitation level that we demand. And if you look at a state with this excitation, you can just compute the correlator in it. Note that even though it looks complicated, because of the approximate degeneracy and the linearity in n of the spectrum, the calculation ultimately is not horrendous. It's a very complicated, or not very, it's a complicated harmonic oscillator type calculation. That's what we are to compute the correlator. Okay, so in order to deal with chaos and so on, the details of the spectrum, much more details of the spectrum will be important. But here we are just, we can compute things quite explicitly. So once, and we can compute Whiteman correlators in this highly excited state. And and the punchline is basically what I said already, which is that at this stage, once you get the correlator, you can take epsilon going to 0, and the limit is perfectly well defined. There is no approximation, and there's no, there's nothing that we have to manage further. The explicit correlator that you get, if you have been keeping track of the normalizations, etc., I started like 5 minutes late. Oh. So epsilon going to 0 limit, the limit is well defined, and the result is precisely the Hartle-Hawking correlator is what we find in the epsilon going to 0 limit. Okay, so so there are some technical facts. Let me ignore it because Shailesh will get mad at me. So yes, so the observation. So one observation is that the Hartle-Hawking correlator is an exponentially decaying correlator. So it's a 2-point function. You're perturbing the system at some point and then measuring the response at some later time. And the time difference between the two, the correlator decays exponentially. Okay, so the point is that this is an indicator of information paradox if left unchecked. Okay, so if this decay keeps on going, it means that the correlation function is dying to 0 exponentially for arbitrarily long times, and this is sometimes called Maldacen information paradox. So, but the point is that in our case, it is not this, the Hartle-Hawking correlator is only an approximation in the small epsilon limit. So if you keep epsilon finite, what you find is that precisely at this time scale of the order S time scale, which is basically what is called the page time for these kinds of systems. So at the page time, what you find is that the correlation functions are overtaken by noise. Okay, essentially because we are working with a very highly excited state, so it's a very essentially random state. And that's where we are going to end up once you get the correlator, when the time scale becomes that's where you get. So this is the main statement of this slide, which is that if we keep epsilon finite, which is essentially the same thing as keeping n finite, and take t going to infinity, there is no information paradox because we have a perfectly unitary correlator, and it just, it goes to exponentially decays, and then there is noise. But on the other hand, if we send n to infinity, it is basically epsilon going to 0, you end up with the Hartle-Hawking correlator, which shows information paradox. Okay, so that's this is not super surprising because the horizon is what is causing information loss. So if you cut off the horizon, you're not going to lose information. It's just it's just a quantum field theory in a box. Essentially, the box has is close to the horizon. One of the walls of the box is very close to the horizon, but it's still a unitary box. Okay. So now let me come back to this statement that I made about Leutheusser and Liu. So the Leutheusser and Liu, basically what they said, I'll just say it qualitatively. I mean, my student is the expert on this algebra business. I'm also not, a super this thing. But so the point is that so the question is, if you start with a single CFT in the holographic system and you have a large n limit, what happens? So how do you find the interior time of a black hole? How do you get the black hole to have, let's say, interior time evolution? So, and the idea here is that in the large n limit, the single trace sector of large n gauge theories in these thermophile double-like states undergoes a phase transition, and the algebra of operators goes from type 1 to type 3. And type 3 algebra this very crucial property that they have what is called a commutance. So let me just draw a picture. So these sounds very fancy, but my understanding of it is also quite phenomenological. So this is your, let's say, some one-sided CFT. Okay. So, and you have a bunch of single trace operators here, which corresponds basically to light fields in the bulk. So, in the large N limit, if you start with a thermofield double or a highly, with the thermofield double, what happens is that the algebra of operators basically becomes type 3, and type 3 algebras have this property that there is a second region, there should be a complementary region that automatically comes with it. So essentially the type 3 algebras are algebras that correspond to subregions in quantum field theory. Okay, so which means that the type 1 algebras on the other hand are associated to full Hilbert spaces of theories, and type 3 corresponds to subregions. So which means that the so the second region, so once the transition happens to type 3, it is natural that you have a second region, and that's what is essentially manifested by our in our epsilon going to 0 limit, where we had initially a quantum field theory on one side, but when epsilon goes to 0, you have the possibility of analytically continuing into a new region. So this is the picture. So yeah, so our emergent Hartle-Hawking correlator results are natural from the type 1 to type 3 transition perspective. And so yeah, so this is because the Hartle-Hawking correlator was one of the reasons for Leutheuser and Liu to suggest that the transition happens to type 3. Okay, so yeah, so let me just skip this slide. It's not super important. Yeah, so let me make a couple of comments based on what we are seeing here. So the key point is that the Hartle-Hawking correlator loses information after the page time, which is order S time scale. So one of the ways in which people have constructed interior operators is by using, so what they do is that you take a finite N theory, but then postulate the existence of a crustal time. Okay, so this is sometimes, this was done by Papadodimas and Raju, and this is the construction of the interior in that is, in generally, it's the question is whether this construction is a valid construction of the black hole interior at late time. So our calculations, it's not directly related, but it's very suggestive of, very suggestive of how it works here. So the key point here is that, so there is, in the Kruskal time, even if you hardware a Kruskal time at finite N, what happens is you have a finite page time. Okay, and that means that the correlator is losing information after that time. But the Leutheuser-Liu like constructions which do not postulate a Kruskal time, right? So what happens to them in that case is that the n going to infinity is crucial for them to have an interior. That means that in the n going to infinity limit, the page time is also infinite. So there is no possibility of interior, there is no talk about post-page physics in the discussion of Leutheuser and Liu. And because of which it avoids this problem of state dependence, if you like. So this the structure is independent of the things that we are saying. So if you have a correlators, if you have correlators that we know that at finite N the correlation functions actually die out and then saturate at some small fluctuations, and so the thing that I mentioned just now is basically a direct indication of the fact that so the post-page discussion using the Hartle-Hawking correlator is it's not really a viable thing. Is sort of the punchline of this, but I'm kind of rushing through this, so it's not really. Let me not. So what was this? Yeah. So let me summarize with these couple of slides. So the principle of equivalence is an EFT statement. There may be no immediate contradiction between principle of equivalence and its stretched horizon if the latter is only present in the UV complete description and its effects are suppressed by the effective correlators. We have not quite done that. We have done it only for exterior correlators and observed that analytic continuation exists across the horizon in the large N limit and has many features. So this is sort of the takeaway point. So the stretched horizon as a UV regulator has this property. Okay, so there are some caveats which, that's another big discussion. So let me leave it here. Actually, yeah, thanks. Sorry. But I think 9:35 is when we start.
Yes, well, we have to start the next talk on time to keep on schedule. So I encourage questions over coffee.
Sounds good. Thank you.